Hi, and welcome to our introductory course on File Permissions Security. This training focuses on Linux and OS X. These two operating systems offer a choice of file systems, most of which inherit the basic file permissions and ownership characteristics of traditional Unix systems. The objective of this e-learning course is to review standard Unix file permission concepts and present best practices that mitigate related security issues. After a short introduction, we describe traditional Unix permissions and SetUID, SetGID. Then we provide some recommended best practices and describe OS X access control lists. In current desktop systems and even single-user machines, multiple background processes, such as daemons owned by system accounts, are present. This means that even if outwardly the system appears to be single-user, in fact, there are other users present. For example, a privileged user that represents the machine administrative functions, and one or more unprivileged users that may have access to the machine. In order to maintain a division of ownership and access control between these distinct users, the underlying file system needs to support permissions on the objects it manages. For example, the FAT file system common in USB drives sometimes does not support permissions, and by default everything is readable, writable, and executable by anyone with access to the files. On the other hand, a typical Unix file system, or a VFAT NTFS file system, does have the capability of giving named ownership and access permissions that the owner of the object can specify to every object it contains, and all files and directories. There are two guiding security design principles to always keep in mind when addressing file permissions. First, economy of mechanism, which states that we should use a mechanism that is as simple as possible to enforce security, but not simpler. Second, least privilege, meaning each process or actor in the system should be given the least amount of privileges necessary to do their job. This minimizes the damage possible if a process is subverted or a user impersonated, for example. We are now going to do a quick review of the basics. Most people are familiar with standard Unix read, write, and execute file permissions and how they apply to files. This is self-explanatory. It gets a little more complex when you talk about the same permissions applied to directories, since there's no immediate semantic meaning for executing a directory. Read and write permissions are still the same. Read enables listing directories, and the write permission allows the user to modify directory entries by creating, renaming, and deleting files, since in Unix file systems, a directory is a file containing references to other files. In order to change the directory, that is, the contents of the file that represents the directory, the same semantics as plain file access permissions apply. Note that this does not give users the permission to change the contents of the files themselves. In the context of a directory, the execute permission gives the ability to traverse into subdirectories. If a directory has only the execute permission to its owner and no other permissions for group or others, the owner will be able to pass through the directory into any subdirectory it contains and to which the owner has rights. But the owner will not be able to list the contents of the first directory, in other words, read permission, or change file names, or add files to it, i.e., write permission. We do not need write permissions on a file to delete it. With write permissions to the file, we could wipe out all the contents of the file, but we might not necessarily be able to delete it. It's possible to both delete a file that you cannot write to, or to write to a file that you cannot delete, nor create, nor rename. Consider the two situations in the examples. A directory containing a file. In the first example, the directory has only the write and execute permissions available to the owner. This permits changes to the directory contents and traversal of the directory. The file has only read permissions to the owner. This setup permits the deletion of the file without permissions to write in it, since the delete operation happens on the directory, not on the file. The second example is similar, but this time the contents of the file can be modified or written to, but the file itself cannot be deleted. Try these examples on a Unix shell and verify the results and behavior, which may change slightly from shell to shell, for yourself. In Unix, every user is part of a group. Files and directories have a user as their owner and belong to a single group, of which the owning user may or may not be part of. The figure shows the use of the ls-l command to show permissions on a file. Permissions are typically stored in the file system in a binary data structure. The common human-readable interpretation used by many, but not all, Linux programs is made up of 10 characters, divided into 4 groups. The first group is 1 character long and represents the kind of file: a plain file, a directory, a char or block device, a hard link, etc. The subsequent 9 characters represent the file access permissions, divided into 3 groups of 3 characters. The first group represents the permissions available to the owner of the file. The second, the group to which the files belong. And the third, to others, users that are not the owner and not part of the group the file belongs to. In each of the 3 character groups, the first character is the read permission. A lower caps R represents the permission is granted, quote, hyphen, quote, that it is not. The second and third in the same way represent write with a lower caps W and execute with a lower caps X. In some cases, there are other representations possible, like for example, the lowercase t representing a sticky bit directory, or lowercase s representing a set user ID or set group ID permission. We'll talk more about this in a short while. In the Linux world, whenever a user wants access to a file, the user will fall into one of 3 categories. The user is either the file owner, belongs to the same group as the file, or neither of these apply. In order to establish the access that will be given to an object in the file system, the permissions are checked in the order user, group, and others. This guarantees that the stricter permissions have priority over the lax ones. Let's look at a quick example. User Dimitri is the owner of file.txt, and by looking at the output from ls, you'll notice that the owner of this file does not have read permissions on it. However, Dimitri is also in the group that owns this file, wheel, and the group has read access. Does that mean that user Dimitri will be granted read access through the group? The answer is no. Dimitri will not be able to read the file. The algorithm stops at the first match. If the user is the owner or in the same group that owns the file, the remaining checks are not considered. Note that the owner of a file has the rights to change permissions on it. This is the crucial permission of an administrator or a superuser. Therefore, although the user cannot read this file, she can grant herself read permission and then proceed to read it. As we've previously mentioned, the execute permission on directories allows us to access objects inside directories, provided we know their names beforehand. On the other hand, having only read access on the directory enables us to see the directory contents, but not to access it. In this example, the ls-l command can read the directory entries, but since the user does not have execute permission in the directory, the objects within cannot be accessed. We've already seen the permission denied message when we try to access some files. So when does the system check permissions? This depends mostly on the file system in use. Although most file systems export a uniform interface to the user and to the system, at a lower level their behavior may differ. For most local file systems, such as HFS Plus on the Mac or ext 2, 3, or 4 on Linux, file permissions are checked only when the file is opened. For network file systems such as NFS, this may be different. This can lead to very subtle bugs called talk to, or time of check to time of use. Make sure your program's behavior is consistent and secure across all file systems, assuming worst-case behavior and making sure your program works in either situation. The security implications of the timing issue are exemplified here. A SetUID program uses the access system call to check for permissions to read a given file. Because access uses the real user ID and not the effective user ID, the call will return the expected answer, even if the program running it is running as root. Between the time the access call happens and the open call proceeds to open the file, an attacker will create a symbolic link to a target file that she couldn't usually access as the unprivileged user. This can be done by running a tight loop that creates and removes the link, while at the same time running the vulnerable program as well. After some time, the conditions are met, and the file that gets opened is the one pointed to by the link. This problem is also known as a race condition. This issue is difficult to eliminate completely due to the semantics of the system calls involved. This example is presented here as an extreme case of file permission and ownership circumvention, and a full discussion is out of scope of this introductory course. Much information is available on the web. The commands used to configure file permissions are displayed on the table. chmod is commonly used by the owner of a file to change the file's permissions and give or deny access to other users. The other two commands are usually only available to super users. However, there is one exception. The owner of a file can use chown or chgroup to change the group of the file as long as he also belongs to that group. For example, if the user owns fileexample.txt and belongs to the group staff, then she can make example.txt also belong to that group using either chown or chgroup. This functionality enables a normal user to easily share her files with coworkers in the same group. It is not possible to change ownership of the file, though. The reason for this will become apparent when we consider the SetUID bit. Most Linux users are familiar with the two forms of change mode syntax, symbolic and octal. They are equivalent in all forms, but some users prefer one form or another for readability reasons. Please refer to your chmod manual page for details. Symbolic links are files containing absolute paths to other files, handled in a special manner by the file system. They behave in pass-through mode by changing their permissions to the ones of the files they reference. The only exception is that the owner and group is that of the link itself. Hard links, in essence, are two directory entries pointing to the same inode, and changing the permissions on the inode through either entry affects both directory entries at the same time. This can be seen in the example. In the case we've seen before, where a directory has read permissions but no execute permissions, a symlinks into such a directory cannot circumvent the lack of execute permissions, since symlinks are just alternate paths. On the other hand, a hard link will circumvent this situation, since they are actual references to the underlying file system bookkeeping structure, and as such, access from other directory entry will be allowed. We have previously mentioned the SetUID and SetGID bits, which appear as S in the permissions representation. SetUID works on executables. It is ignored on directories in Linux, but for binary executables, if the SetUID bit is set, the executable is ran with the effective user ID of the file owner, instead of the current user that actually invoked the binary. So if an executable is owned by root, but run by user Dimitri, it will execute with root privileges. The SetUID bit in shell scripts turned out to be such a security nightmare that this bit is ignored for shell scripts in most Linux distros by default. This behavior can be modified, but it is highly recommended never to run a SetUID script. The SetGID bit works in much the same way for groups. A SetGID process will execute with the effective group ID of the file owner. Things work a little different for directories. As we mentioned, SetUID is ignored for directories in Linux, but when SetGID is on a directory, any files created on that directory will inherit group ID from the directory rather than the file's creator. This was originally used to make it easy for people to share files within their group. OSX and FreeBSD can be configured to interpret SetUID on directories analogously to SetGID. This is mainly to force all files and subdirectories to be owned by the top directory owner. In other words, this allows you to create a file in the directory and have the file's owner and group be immediately changed into something else. For example, a log file can become root-owned. Unfortunately, apart from what's shown on the table, any other SetUID and SetGID functionality is not portable across systems. When using the ls-l command, SetUID and SetGID bit are displayed as S entries in the corresponding execute bit. A lowercase entry means that the execute bit is also set. The uppercase means it is not. SetUID bits are dangerous because they enable a local attacker to pretend to be someone else that may have higher privileges. In other words, SetUID executables that have bugs that lead to local privilege escalation. The SetUID executable have historically become a huge security headache. Attackers target them because they know they can get root privileges if they can subvert them. If your design includes a SetUID executable, you can become a target of a local attacker trying to escalate privileges. An excellent reference to all the details of SetUID is shown on the slide. Another special bit is the sticky bit. It is used mostly on directories where either groups or others have write access. It restricts write access by only allowing the owner of a file to delete it. Renaming a file is considered equivalent to copying and deleting the original and is also not allowed by the sticky bit. Although this bit prevents others from deleting the file, simply modifying a file's contents still depends on the write permission on the file itself. The sticky bit is not portable across all Unixes. It works for Linux, OS X, BSD, AIX, but not of HP Unix. The sticky bit is displayed as a T in the position of execute bit of others and follows the same convention. Let's consider now the application of some of these bits. Assume that we want a safe temporary directory that multiple users in the same system can share. Which permissions should be set for this to work? There are at least 4 ways that a malicious user of a system can attempt to disrupt another user's workflow. The first attack is simply to change any temporary files created by other users and placed in this shared temp directory. To avoid this, each user should simply remove write permissions for groups and other on the files they create inside the temp directory. The second line of attack is to delete another user's temp files right after they are created. We can avoid this problem by also setting the sticky bit on the directory. Then only the file owner will be able to delete the temp file. A third attack occurs when the attacker creates the file, maybe as a symlink, before the victim does. If the attacker can get ahead of the victim, he will trick the victim into using a file that he owns and will be able to delete or tamper with it. A way to avoid this attack is to make the file names unpredictable. One final threat is information disclosure. An attacker may find out important information just by seeing that there are temporary files there. You can find out, for example, if the root user is logged in. To prevent this, we also need to make the file names unpredictable and give everyone execute but not read permissions on the directory. There's an easy way to remove some permissions on newly created files by default using the Umask setting. In summary, in order to have a shared temporary directory that can be used by multiple users, you have to set the sticky bit and remove the read bit on the directory, and then only use completely random and unpredictable file names, and remove any permissions to groups or other on those files. This is very error-prone, and a good alternative is to use per-user temporary directories. If you cannot do so, then the link on the slide has some more guidance. By default, all users have a default set of permissions that will apply to each new file or directory created by that user. This is the default mask, so called because it acts as an effective bit mask to decide on the actual set of permissions a file will have at creation time. This system-wide mask is usually too permissive, unless the software explicitly sets something else by way of the Umask. The Umask specifies what permissions to remove from the system-wide default every time a file or directory is created. It is either inherited from the login process or set in the initialization file for the shell used by the particular user, or it can be run manually. The Umask is inherited from parent process to child process. The process can change its own Umask at any time, and the Umask can only restrict privileges, not grant them, by using the Umask system call. Try setting your Umask to 077. This means only the owner has access to newly created files and directories. The Umask is binary OR'd with 777 for directories and 666 for files to achieve the final permissions set on disk. This default is safe as other users cannot tamper with or read your new files. Most systems default to an unmask of 022 that only removes write privileges and is too loose, as the result will be a 655 permission for files, which means read and write for the owner and read for group and other. This does not satisfy the least privilege principle in most cases. Mac OS X systems 10.4 and newer have new access controllers that further enhance the system's configuration. Not only can we specify access controllers for each resource, but the newer permissions are far more fine-grained than just read, write, or execute. Each access control list, or ACL, is made up of many access control entries, ACEs. The ACEs allow or deny access to a resource to a specific user or set of users. The order of these entries is important, and this newer mechanism takes precedence over standard old Unix permissions on the Mac. In accordance with the principle of economy of mechanism, we recommend you avoid using it. There's usually a simpler way to achieve the same thing without using it, and it is not portable. Only use it if you really must have the extra granularity. Linux has additional kernel modules offering the same functionality. One part of ACL that can quickly become tricky is inheritance. Inheritance propagates permissions down a directory tree when files are created or when access control entries are changed. Be sure to inspect the effective permissions of your system thoroughly if you're using ACLs. We've come to the end of this course and just have a few final rules of thumb. First, try to manage your user's access through groups. This usually makes life much simpler. Second, use per-user temp directories whenever possible. And third, remember to be very aware of the permissions of your files. Do not forget to examine edge cases for possible failures, and keep in mind the possibility of file system changes between the time permissions are checked and the time they are used. And don't forget to follow the secure design principles of least privilege and economy of mechanism, as described at the beginning of this module, and have a clear and well-defined schema for your file permissions. Thank you for joining us for this introductory course on file permissions. For those looking to learn more, we have listed some additional resources on this slide.